Hey, good morning, friends and neighbors. I was asked for my opinions on the TEPCO General Electric Fukushima disaster in 2011. I have been following that accident very closely. I've been following nuclear research, nuclear detection, nuclear accidents, nuclear studies from way back. Uh, it would be the beginning of the Manhattan Project. The sciences and the training that I had began when the sciences began because all this research began long before that. Um, so this is built on the shoulders of giants. This is what we do. So my challenge with talking about Fukushima is honestly the audience that you're trying to speak to. So when I started trying to put together this presentation, okay, I've got connection problems, so it's going to be coming and going, and this is going to be a moment. So here's what I'm going through, and I could spend years redoing just to try to build this presentation up or this conversation up. Anyway, here goes. I'm going to give it a try. The Fukushima disaster was the third major commercial nuclear accident that we know about on the globe. Now, honestly, there is no distinction between nuclear accidents or nuclear weapons. This is all the same sciences and physics. It's decay physics and high energy particle physics and inverse squared laws and other things of that type that are all put together in matter and are interleaved, and one weighs on the other. So, so here was where I first started. A simple Google search, but you have to be rather specific in your searches or you get too many results back. So using enough keywords to get a reasonable return is important. So the first search string is, and search along with me, folks, is go to any. I'm using Google, but use any web search and do a TEPCO Fukushima release inventory. So this is the first thing after any type of release, whether it's nuclear or if you go look at the Baytown Freeport um, chemical plant fires, those releases in the air, in the ground, into the ocean are fairly well understood which direction they're going to go based on the wind and the burn and everything else. So those are these plume maps I've discussed before. Gaussian distributions, Poisson distributions, things like that can help model what we expect from these accidents we know so much about and just don't want to know about. So TEPCO, Fukushima Release Inventory, that first search, and I would go through probably about 10 to 20 of these strings just to put together a conversation about TEPCO. So here's the first string return, TEPCO, Fukushima Release Inventory. It returned only 48 results. This is a partial tell in that it probably should have returned a whole lot more than that. But my keywords are working because I didn't get a million results back. I'm trying to be a little bit specific here. So I've got 48 results. So which of these 48 do I point to have the discussion? Well, what I was going after is the release inventory. So my first lineup is estimation of radioactive material released to the atmosphere during ... Uh, this is a May 26, 2000 document released by TEPCO. I'm going to speak in detail a little bit to the top hits I'm not sure exactly what the return criteria was. This is probably by popularity, maybe. Doesn't matter. There's only 48 results here to page through for a first scan. So all I'm doing, I'm basically looking for this release inventory. What should happen with these inventories, and it is being done, we just don't have access to the information, is the initial release is estimated, the possible travel paths, air, water, soil migration is considered, and a map can be drawn up for each of those spaces individually, or some type of combination map can be drawn up. So that's the first step, is estimating where this pollution went to so that you know what to do about it. If you go look at how assessments are made for hospital placements and hospital funding, that actually is a consideration. If a nuclear plant is going into an area, the ability for the health services to respond to an accident can get funding for a hospital in a state or a few hospitals. It depends on who's doing the analysis and the begging, pleading for money argument. So there you go. This is how easy it is to get off into a side conversation about a simple question. What about Fukushima today? So when I got to this first page, my first search page, to again build up an information set, an understanding of what I want to speak to, I'm looking at again, estimation of radioactive material release. That's from TEPCO. Another one from TEPCO. Result of radioactive analysis found. There's no date on them. I'm not opening these individuals up. I've been through a lot of them for many years. TEPCO release, press release, release of nuclear main party involved. TEPCO release, estimated amount of radioactive, estimate of Fukushima derived radio cesium in the North Pacific. That's decided by the National Institutes of Health. Institutes of Health is watching this because if we need hospitals, they will go in behind the scenes conversations and debate with the people who do funding and allocation grants, right? You know, this is federal government. There's no I suppose a hospital, they are going to get involved. It's going to be privatized. The hospital's going to go to corporate wealth, and we're going to pay for whatever happens from it. So let me get back to my list, because it's just so easy to, again, get diverted from a main conversation. And this is what I'm trying to point out, really. Estimate of Fukushima derived radiocesium. TEPCO ice wall fails to freeze Fukushima's toxic water buildup. Okay, so this one is part of the story. I am reasonably impressed that that ice wall was made so quickly. We do ice walls. That's a mining technology we've used for a number of years. It's still being used. It will be used because you can freeze the water so it doesn't flow into your drilling operation. You can freeze the water and the soil to make it solid enough to drill out rather nicely and not slump and fall down on you, so it's not mud. And you can shore up underneath buildings and other structures until you get the superstructure of a tunnel built. So this is a useful technology, and that they deployed it at Fukushima is interesting. It was the first test of this type of thing that we know of. They you could go look at the heat energy potential of the fuel in the reactors and get some idea, and you could do some good maths on it to get a real good idea with a high confidence level how much heat energy was in those fuel bundles. It will be for their half-lives. For what, 7 to 11 half-lives is considered enough decay to get near something. Don't buy that, but work with me. So TEPCO's ice wall fails to freeze. That each one of these could lead to another set of search terms and another tab open for me to go down and discuss. So let's spend a moment on the ice wall. Um, the ice wall was truly a no other alternative bid. They could have put a solid wall in, and you might think that they should do that in front of the ice wall as a secondary diversion. So the challenge on putting a mechanical block like that there, a wall on the upside of the plant or any part of that, is the geology in the area is flawed. It was a design basis flaw they marginally knew about, just like they ignored the wave on the cliffs behind the plant that showed a tsunami had struck that area within human visible time frames, million years ago maybe, but we're that old. So that was a tell that somehow got ignored. We knew, and you can go back to the engineering design drawings, I'm using the figurative we here, right? Men and women in the room knew that a wave had hit there previously. They knew there was a probability of it happening again, so you're getting into statistics and heuristics and other mathematical things. All of these considerations roll into a risk analysis document somewhere within the engineering process, because this is engineering, not prayers. And these things, if the processes are followed, the processes work, because that's why we build skyscrapers. That's how we build skyscrapers. So, ice wall. They put the ice wall in, and you can go back, and this would be a Google on Fukushima ice wall, TEPCO Fukushima ice wall. Um, and maybe we'll do that next and see how many returns we get for it. But each one of these takes a quick walkthrough, because there are topics. Again, radiation is cumulative, right? It's additive. It doesn't go away, it decays away. But until that happens, it is additive. Yesterday's plus today's equals your exposure. So the ice wall did not work for a long time. It was struggling. They had to increase the BTUs to it. So this thing is a refrigerator in the ground trying to freeze water that's being heated by the fuel that got released to the environment that's still in the ground there. So that's the first challenge. What's the water temperature down there in the hole? So you're trying to freeze water from 50 degrees down to freezing point, 30 something degrees maybe, or zero if we're doing the Celsius. So there is a records through time specifically about the ice wall and its failures and how long it's taken to get to, I think it's at about a 90% efficiency now. What is the ice wall doing? The ice wall is containing groundwater from circulating with those three melted cores that are in the soil around those reactors. So the soil has a potential to leach anywhere, and it will, and it has, because the ice wall didn't work for a long time. You couldn't put a solid wall up there behind that on the backside, because there is a river flowing. Second engineering failure. When they started digging into that hillside to build the plant closer to sea level to save money, they discovered there was a natural aquifer coming from all the Japan behind it and the mountains, and it had a pretty good force, and so it was flushing water through that area, period, underground, no cesiums, right? So now that water is flushing hundreds of different radioactive materials called isotopes. These are isotopes of elements on the periodic table, so they're twins or whatever you want to call them. And these, very simply, like putting tang in drinking water, get dispersed and float out into the ocean. They get dispersed deep into the soil. So that's a problem, because even when these things decay, they leave heavy metals and other elements that are not natural to our biome, which is the Earth, the planet we live on. So the ice wall fails were, to me, not unexpected. The reporting on it was very slow because they don't want to realize how unprepared this global industry was for this accident. Okay, this is engineering design failure, poor risk management processes, poor conversations with the public about the true risks. So, engineering failures up front in a design basis and the design reviews through the process, these things aren't dead. You continually review engineering work through the process. Um, Experience working with Bechtel, Fluor Daniels, 5 to 7 other major, huge engineering houses that do cities and infrastructures and superstructures across the globe, big engineering houses. When you dial them and the phone gets picked up, you are being billed. Good money, good people, good engineers, very large, very structured firms with deliverables. So TEPCO's ice wall was engineered by somebody. If you find that somebody, you can go chase out that and find more out about the ice wall's wins and failures. What isn't talked about in the ice wall is how much energy it's taking to freeze the soil around there. That soil has to be frozen for 7 to 11 half lives of the nastiest radioactive materials in there. So it's going to take another nuclear reactor to power. Oh, so we got some homework to do. This isn't going to get fixed overnight. Stop that. Long term stuff for your grandkids, you know. All right. So the ice wall has had failures. It still isn't 100%. It is huge risks. It's a huge cost to run, and taxes are paying for it. If TEPCO is billing their customers, that is a tax on almost all the population of Japan to pay for the follies and the profits of what we've done. So it's done. That sucks. It's done. We learn, get better. We're old. So TEPCO's ice wall fails to freeze. How many minutes did I just spend on that? This is going to take a while. So thank Google for putting the storage up there. So we'll see what happens. Spatial and temporal distribution of 134 CS and 137 CS derived from. This is a 2016 document by rsc.org. Optimal interpolation analysis was used to investigate. Now, you know what optimal interpolation analysis means, right? Interpolation is a very interesting word and matters in the audience. Interpolation is a loose thing you use to make Donald Trump speeches and Gordon Jordan, whatever, the lobster freaking dude speeches. So when the lobster uses words like that, they're meaningless. When somebody that understands the word uses the word, interpolation means that you have taken data and changed it into a relevant measurement to what you're speaking to. And you have to do this because Europe speaks in centigrade, we speak in Fahrenheit. So that is an interpolation of a number. If I say, 32 degrees is 0 Celsius. Okay, that's an interpolation because my mind just did that quickly and it knows 0 equals 32. What? Okay, so that is an interpolation. If I was giving a conference somewhere and I said that to the audience, they would understand and they would know that they could go back and look at the raw data of Fahrenheit and convert that themselves or quickly interpolate it into another meaningful number so that I can bake a cake because I don't know what the oven temperature is supposed to be. So there's interpolation. Chefs do this stuff. You do this stuff all the time. It's how that word is used. So now the takeaway here, CS 134 and CS 137 are two of the hundreds of isotopes you will find mentioned in the release inventory. So 134, 137 is good. I could use interpolation with those numbers against the rest of the release inventory to say, oh, if I'm seeing a ratio of 134 to 137 cesium here, I recognize that as being from Fukushima. And because of the release inventory, that means that also in the air with that 134 and 137s are maybe 100 of those 200 isotopes that were released. So this number, this spatial and temporal distribution could be interpolated into the full assay, the full isotopic list of the area for reasonable assessment of the efficacy of human habitation, as an example. The animals are harder to stop. So right now I'm at 20 minutes, and all I've gotten through is the first of digging up the information to be able to speak to the TEPCO Fukushima Daiichi plant's nuclear disaster. It was a massive engineering failure that we can talk to and speak to as a perfect example of when things go wrong. Okay, the other two nuclear accidents I spoke to, Chernobyl and Fukushima, were also engineering disasters, hidden, buried in the discussions. Those two plants had mixed oxide fuels. Mixed oxide fuels inside the reactors respond differently to tuning changes. They respond much quicker in some cases or much slower. So when the operators are informed that they have MOX fuel in the reactors, their mind instantly says different, if they're trained, different response mechanisms, spidey alerts, you are on edge now because you know that there's a higher risk of something going wrong, right? That's the odds. That's what we know about the business. So the operators in both of the other accidents, Chernobyl and 3 Mile Island, were caused because the fuels, when the reactors were being tuned and changed to increase output, the control rods were moved 3 inches, and the operator waits to watch all the responses of the reactor. He's given a chart to watch to say, okay, because of the heat exchange systems in here and the large cavities and boilers in between, right? That's not just one reactor. This is a full system and a very balanced system between other chambers and process flows. So a lot going on here. Operator Spidey senses are on. He's watching everything twice as hard as he does, and all the other operators are informed and keyed just because there was a safety briefing in the morning, the beginning of the week, every friggin' day. God, they get old. Did I pay attention? What did I miss? Oh, well, let's go to work. It's a good paycheck. So, spatial temporal distributions of 134, Tokyo Electric Power Company, Wikipedia, Fukushima Daiichi status updates from the IAEA. This is a TEPCO Japan release. This is a 2013 document. Fukushima Radiation Exposure, World Nuclear Association, jump to radioactive releases, and 2 days following, 0.16 of the total inventory. Okay, this one opens up. Now, again, I'm not even opening the articles up. I could pick on them or talk to them specifically, but hey. So jump to radioactive releases in 2 days, 0.16 of the total inventory. I'm going to go back to that release data. The initial quest was TEPCO Fukushima release inventory. right? 4 words I'm looking for. It returned me 80 something documents according to Google. So this is what's popular out there in the Google sphere, and there should have been hundreds of returns, but we can find them another way later. So remediating Fukushima when everything goes to hell. Um, oh, no, no, no. Sorry, I was still on radiation exposure from WNA. So this brief, 2 lines of the article, 0.16% of the total inventory, blah, dot, dot, dot. Okay, in those release estimates, initial release estimate is guesses from everybody screaming, oh my God. You quickly go to reactor inventory documents and you say, oh my God, according to all the models, here's what happened, here's what got released. And then 4 hours later, you get a new update as to the extent of it. And you say, oh my gosh, because there's no gods. Oh my gosh, reevaluate, go at it, team, because this is a team. This isn't one person's shoulders here. This isn't one person there was one person making decisions about who gets to know about shit, but on an engineering standpoint, this is hundreds or thousands of people across the globe trying to communicate um, succinctly about one of the largest radiological releases ever in commercial nuclear history. 3 reactors, 6 spent fuel pools released. The inventory assessments still should be ongoing because we need to improve the sciences and the models so the next time, and there will be a next time, we do better. Okay, so this release inventory information, that alone is a doctorate thesis just to chase that one thing through the years of time. It is a news article on the follies of engineering a disaster after the fact. We did not prepare for this. We had lessons from other nuclear disasters. Before commercial, we had military radiological disasters. We know what this does because we've done it to ourselves. Shame on us. So we need to make it better. All right. So this still is going to be long. I don't know where I am. Looks like I'm about a quarter of the way down the page. So I'm going to keep blowing through these things and stop, and then we'll go from there. Is this useful? Does it make you wonder? Can it help you get a question that maybe you should ask somewhere? Idaho is getting a nuclear reactor. I can't believe it. Saudi Arabia, nuclear. Oh my gosh. The instrument company I worked for, I was a junior, senior engineer in the ranks. And the constant joke was when we had to go back to Iraq to rebuild their optical emission spectral photometer that was managing their reactor inventory information. Again, these things measure isotopes. So anyway, we had one in Iraq's nuclear facility, and it got blown up by the Israelis. I hope the Israelis blow up the Saudis too. They know better. They really do. I mean, it'd be a good test of Israeli hubris, and I couldn't blame them for doing it, but we should stop that without bombs. We can do that. Hell yeah. So, radiation exposure, world nuclear explosion, remediating Fukushima, another joke, another whole nother line. Let's not go there, but I should. That would be about tab 15 now if I've been opening up tabs. So I'm giving you some idea what I've been doing for years following this through, because this is a history, not today. We know how we got there. Remediating Fukushima. When everything goes to hell, clean up Fukushima Daiichi. Fukushima Daiichi accident from WNA. No date on that one. 2017 Fukushima nuclear disaster. Former TEPCO executives go on trial. Why Fukushima was preventable from the Carnegie Endowment. In Fukushima nuclear plant crisis, crippling mistrust Treated water at Fukushima nuclear plant still radioactive, 2018. Estimation of the inventory of the radioactive waste in Fukushima, a utilization of 134, 137 CS in the environment to identify the reactor, nature.com, scientific reports. Radioactive contamination in the Tokyo metro area, unexpected sources of Fukushima derived radiocesium to the coastal from PNAS. PNAS is good reading. Go bug that, man. Analysis of a nuclear accident, fission and activation products, PNNL, again, good reading. NRA's regulatory perspectives on decommissioning to horizontal and vertical distribution of 137 CSs and seabed sediments. So this is a Springer article from 2017, and this is one of many that speaks to cesium migration, because all the information we had about cesium migration, a good portion of it that was available to me is around the and um, Hanford site and all of the decades of remediation work they've been trying to do there. Again, another one, my instruments in another location touched some of their radioactive poisoning in our aquifers. So stories, right? Lots of stories. Keep going, Rich. Horizontal and vertical distribution of 137. So that they're acting surprised, but another article out there, it might not show up in this batch because the search criteria, but another article out there was scientists showing amazing at the speed of cesium migration into the soil, because the studies done out of the Hanford area, this is high desert and alluvial soil, mostly in the Hanford region. So Hanford's soil migration studies did not match the results of migration studies in Japan, because the soil constituency is different and the ion migration potential of these nuclides, because of their valence shell structures, make for different flow through materials. And the soil in Japan is different enough, let's say acidic or base difference, whatever it is in the chemical reaction, has made the cesium actually transport or migrate deeper into the soil. So what that changes is soil plume diagrams and how quickly the cesium is going to migrate through the biosphere. Now understand, in our, let's say, 2 billion years of evolution on the planet, and 7 billion years, fix my numbers, correct me, but I got a big error margin going here. So what we grew up with and were exposed to for the period of our evolutionary process has been altered. It has been altered with elements that we know and understand because people recognize a periodic table, but on top of that, we've added the isotopic conversation. So an isotope looks like its twin on that periodic table element. Cesium looks like cesium, no matter which cesium you're looking at, until it changes into something else. So all these numbers are related and matter, and the study over time, the use of the tools we need for studies over time about this matter. Where I was going with the isotopes is a cesium looks like a cesium. And if you look at the periodic table and follow the cesium column up and down, you will notice that, all right, for this one I'm going to one of my favorite websites. And I will put a link up in here. Periodic table. Okay, I'm missing it. I did a search for periodic table of elements, but go look it up. So cesium ends up being with the list from one search return. And with that, I'm going to take a break, 30 minutes.